3.4. The derivative as a rate of change. The outline of this video is as follows. We will begin by formalizing our understanding of the derivative as an instantaneous rate of change. This concept builds directly on our previous work, with average rates and limits, giving us a powerful tool to describe how a quantity is changing at a single, precise moment. Next, I will show you how to apply this idea in a practical setting by exploring its use in economics. We will define and analyze marginal rates, such as marginal cost and marginal tax rates, to see how businesses and economists make decisions based on the cost or benefit of one additional unit. Finally, we will generalize this concept to understand sensitivity to change, which is a measure of how much a function's output responds to a small alteration in its input. This is a crucial idea for knowing when a small error in measurement can lead to a large and unexpected result in a calculation. Let us see how we can measure a rate of change at a single, precise moment. We define the instantaneous rate of change of a function f at a point x0 as its derivative, which is the limit of the average rate of change as the interval around that point shrinks to 0. This allows us to find how fast a quantity is changing at one specific value, not just over an interval. For example, a circle's area is given by a equals pi over 4 times d squared. To find how fast the area changes with respect to its diameter, we calculate the derivative, dAdd, which equals pi times d over 2. If the diameter is exactly 10 meters, the area is growing at a rate of 5 pi, or about 15.71 square meters per meter of diameter. Notice that a rate of change does not always have to be with respect to time. The key idea is that the derivative tells you the exact rate of change of a function at any given point. Let us see how the derivative gives us a precise language for describing an object's motion along a line. We define an object's velocity as the derivative of its position, s, with respect to time, t, which represents the instantaneous rate of change of position. The crucial insight is that velocity tells us two things: how fast the object is moving and in which direction. A positive velocity means the position s is increasing, so the object is moving forward, while a negative velocity means the position is decreasing, so it is moving backward. Now, speed is a simpler but related idea. We define it as the absolute value of velocity. For a concrete example, think of a car's speedometer. It always shows your speed, a positive number, and does not show a negative 50 on the way back from a friend's house, even though your velocity is negative. The essential difference to remember is that velocity includes direction, while speed does not. To get a more complete picture of motion, I want to introduce derivatives beyond velocity. The first of these is acceleration, which is the rate of change of velocity, or the second derivative of position with respect to time. It tells us how quickly an object is speeding up or slowing down. The next derivative is jerk, which I define as the rate of change of acceleration itself. A large jerk means the acceleration is changing abruptly, which is why a city bus ride can feel jerky even at low speeds. For a classic example, an object in free fall has a position given by s equals 1/2 g times t squared. Its acceleration is therefore the constant g, which is about 9.8 meters per second squared. Because this acceleration never changes, its derivative, the jerk, is 0. So, the key idea is that acceleration is the rate of change of velocity, while jerk describes how smoothly that change occurs. Let us practice interpreting a velocity versus time graph, which is a very different skill from analyzing a position graph. First, We can determine the direction of motion by looking at the sign of the velocity, or whether the graph is above or below the horizontal axis. A particle moves forward when velocity is positive, like in the interval from 0 to 3. It moves backward when velocity is negative, as we see from time 3 to 5, and stands still when velocity is 0. Next, to see if the particle is speeding up or slowing down, we look at its speed, which is the absolute value of velocity. The particle speeds up when the graph moves away from the horizontal axis. For instance, from time 3 to 4, as it becomes more negative, slows down when the graph moves towards the axis, like from 2 to 3. A common point of confusion is to look at the slope. Remember, the sign of the velocity itself tells us direction, not the slope of this particular graph. The key is to read the graph's value for direction and its distance from the axis for speed. Let us use our knowledge of derivatives to solve a classic physics problem, finding the maximum height of a projectile. We begin with the equation for the rock's height, which is s equals 49t minus 4.9t squared. To find the rock's velocity at any moment, we take the derivative of its position, which gives us the velocity function v of t equals 49 minus 9.8t. The crucial insight is that an object launched upward reaches its highest point at the exact instant its vertical velocity becomes 0, just before it starts to fall. Therefore, we can find the time of maximum height by setting the velocity equation to 0. Solving 49 minus 9.8 t equals 0 tells us the peak occurs at exactly 5 seconds. Finally, we substitute this time back into the original position equation to find the maximum height, which is 122.5 meters. The key takeaway is that we can find the maximum value of a quantity by identifying where its rate of change is 0. Next, let us find the rock's velocity and speed at a specific height, which requires us to first find the times it is at that height. To find when the rock is at 78.4 meters, we set its position function equal to that value. This gives us the quadratic equation t squared minus 10t plus 16 equals 0. Solving this equation yields two different times. T equals 2 seconds on the way up, and t equals 8 seconds on the way down. Now we can substitute these times into our velocity function. At 2 seconds, the velocity is a positive 29.4 meters per second, indicating upward motion. At 8 seconds, the velocity is a negative 29.4 meters per second, showing it is moving downward. The speed, which is the magnitude of velocity, is the same at both moments, 29.4 meters per second. The key takeaway is that an object will pass the same height with equal speed but opposite velocity. Let us see how the concept of a derivative is applied in economics, where it helps us analyze changes in cost. Economists use the special term marginal to refer to a rate of change, which we know is calculated with a derivative. Therefore, the marginal cost is simply the derivative of the total cost function, C, with respect to the level of production, x, written as dc/dx. This value gives us the instantaneous rate of change in cost at a particular production level. Because of this, we can use the marginal cost as a powerful approximation for the cost of producing just one more unit. For example, the marginal cost at a production level of 500 items gives a very close estimate for the actual expense of producing the 501st item. So, the derivative dc/dx is approximately equal to the actual cost difference, C of the quantity x plus 1 minus C of x. The essential idea to remember is that marginal cost is the derivative of the cost function, and it estimates the cost of the next unit. Let us now apply our concepts of marginal cost and revenue to a concrete business scenario involving a radiator shop. We begin with the marginal cost, which we find by taking the derivative of the cost function. This gives us the expression 3x squared minus 12x plus 15. Since the shop currently produces 10 radiators, we evaluate this derivative at x equals 10, which results in a marginal cost of $195. This is our estimate for the cost of producing the 11th radiator. We follow the exact same process for revenue. The derivative of the revenue function is 3x squared minus 6x plus 12. At a production level of 10 units, the marginal revenue is $252. Therefore, producing and selling one more radiator is a profitable decision because the expected revenue of $252 is greater than the expected cost of $195. We can use the derivative to measure a function's sensitivity, which tells us how much its output changes in response to a small change in its input. A function is considered sensitive when a tiny adjustment to the input variable, x, produces a large change in the function's value, f of x. The derivative, f prime of x, is our precise measure of this effect. For example, in genetics, the proportion of peas with smooth skin, pesky, is related to the gene frequency, p, by the function y equals 2p minus p squared. Sensitivity is its derivative, dey dep, which equals 2 minus 2 page. When the gene frequency p is small, near 0, the derivative is close to 2, meaning a small increase in the gene's frequency has a large impact. But when CEP is already large, near 1, the derivative is close to 0, and the same small change has very little effect. So, the magnitude of the derivative tells us how responsive a system is to change at any given point. Let us summarize the core idea we have been exploring. The derivative gives us a powerful way to measure the instantaneous rate of change of a function. We saw how this applies directly in physics, where velocity is the derivative of position with respect to time, and acceleration is the derivative of velocity. This tells us precisely how an object's motion is changing at any given moment. We then extended this idea to economics, defining concepts like marginal cost or marginal revenue as the derivative of a cost or revenue function. This provides an excellent approximation for the change that results from producing or selling just one additional unit. Broadly speaking, the magnitude of the derivative indicates the sensitivity of a function to its input. A large derivative means the output changes significantly for a small change in the input. The essential takeaway is that the derivative provides a universal language for describing rates of change in any field. Let us wrap up by applying our understanding of derivatives as rates of change to a couple of practical problems. The first question involves the physics of motion, where you will use a given position function to find the specific time at which a particle's velocity is 0. This requires you to recall that velocity is the derivative of position, so you will need to calculate that derivative and solve for the time when it equals 0. The second question shifts to an economics context, using a company's cost function. Your first task is to find the marginal cost at a production level of 100 units by taking the derivative of the cost function. Then, you will explain what this value represents in practical terms, which is the approximate cost to produce the very next item, the 101st unit. These questions are a great way to practice connecting the abstract math of derivatives to concrete, real-world meanings.